consider again the sphere, a sphere with shape Q. A sphere with a shape Q is uniformly distributed inside. But now we want to calculate the electric field inside the sphere. Example, we want to calculate the electric field here at a distance r from the center of the sphere. Okay. To solve this problem, we also assume the spherical symmetry. The spherical symmetry. That is, if we construct a spherical Gaussian surface inside the sphere, spherical Gaussian surface inside the sphere that is that has the same center or concentric with the object. Okay. From the symmetry, we should have that at any point on the sphere. When we look around, if we are here, or here, or here, or here, and when we look around, we must see the same chart around ourselves. Okay? Because this is because of the spherical symmetry of the system. Okay? So, what we should expect is that it's the same as in the previous example. That is, first, the magnitude of E should be a constant on the Gaussian surface. Okay, mean that if you are at this point, or at this point, or at this point, you should see the same electric field. Okay, this is because of the symmetry. And the second is that, again, E point in the radial direction is the same as in the previous example, that we should expect that E point, if the charge is positive, E must point outward in the radial direction, but if the charge is negative, E must point inward, but also in the radial direction. This is because the symmetry. So, we must have that if we draw the vector dA, we have that dA. Okay. It means that if we want to calculate the flux, the total flux that passed the outer surface of this Gaussian surface, the outer surface, the outer side of this Gaussian surface, if we want to calculate the flux, we must have that phi E is equal to the integral over the closed surface of E dot dA, which is equal to integral of E dA, and again E is a constant, we can put it outside the integration, so we have the E, this is the E integral of dA, and the integral of dA is the surface area of the Gaussian surface, so we have E times 4 pi r squared. Okay. But in this case, the difference is that if we want to apply the Gauss law in this case, this must equal to the Q net over epsilon 0. But in this case, Q net, when we use the Gauss law, the Q net is the charge inside the Gaussian surface. So in this case, the Q net is not equal to Q. It's different from the previous example because in that case, we construct the Gaussian surface outside the object. So the Q net is the charge of the object, but in this case, we construct the Gaussian surface inside the object. So the Q net is only the charge inside this surface. Okay. So we have to calculate the Q net in this case, but that is not hard, because in this case, since we say that the charge is uniformly distributed in the sphere, so we can calculate the charge density. Charge density, rho, which must equal to the Q over the volume of the object, which is the 4 over 3 pi a squared. Here, A is the radius of the sphere. Okay, so this is the charge density. Now, when we want to calculate the Q net, the Q net is a charge inside the Gaussian surface, and this is a spherical Gaussian surface with the radius of r. So the volume of the Gaussian surface is 4 over 3 of pi r cubed. Sorry, change. This is a cube. Okay. Now, if we multiply this volume with the charge density, this term is the Q net, right? The rho times 4 over 3 of pi r cubed is the Q net. So the flux is equal to the rho over 4 over 3 pi r cubed over epsilon 0. Okay, so from this relation we have that E is equal to the low over our time R, okay, over 3 epsilon 0, right? Because if we put this term, take this term to this side, okay, 4 pi cancel with this 4 pi, and this r square cancel with this, not cancel, we cancel with this r cube, and we have r left here. So E is equal to log r over 3 epsilon 0, which is, if we substitute this log, okay, we must have that this is equal to the Q R over 4 pi epsilon 0 AQ. Okay, so this is the electric field inside the sphere. It means that the electric field here is valid when AR is less than A. Okay, or we can use this equal to R is less than or equal A. But in the previous example, this expression is valid when R is larger or equal to A, where A is the radius of the sphere. Okay. It is interesting that if you want to calculate the electric field on the surface of the sphere, okay, you can use both relation. It means if you want to calculate the electric field here on the surface of the sphere, you put R equal to A. Okay, and from this equation, you have that E equal to Q over 4 pi epsilon 0 A square. This is from the calculation that we assume that the point of interest is outside the sphere or just at the surface of the sphere. And when you look at this relation, you can see that if you want to calculate the at the surface of the sphere, you put R equal to A here, and we have the same expression. So this confirms that our calculation is correct, because we must have the same value of E. It's not depend on the way that we calculate E. We must have the same value. Okay, so our calculation is correct.